The last thing we're going to do is take a look at the span of these three vectors, and we're going to try and describe this. So some of the options for types of spans that we've seen in this chapter, in this section, are spans could be just the zero vector. It's definitely not that, because we have some non-zero vectors, because we're building all linear combinations of these guys. It could be a line. We know that's not the case because we have multiple vectors that aren't linear combinations of each other. Could form a plane, or it could express all vectors in R3. So every vector in R3 might be a linear combination of these three vectors. So we know that it's definitely not the zero vector, and it's not a line, because we see these two vectors, for example, are not multiples of each other. And so our question is, do we see like a plane? Do we see all of R3? So there are a couple of ways we can approach this. One is to take a look at at the reduced row echelon form of the matrix that is built from these three vectors. Okay, so let's try that. Let's take a look. So here we have 3 rows and 3 columns, and we're just going to add in our entries. -6, 0, -2, 4, -1, 2. And we want to know what's the reduced row echelon form. If we see that this reduced row echelon form is the identity, in particular, if there are no rows of all zeros, then we'll know that we can write every vector as a linear combination of these three. But we see there's a row of all zeros. Right? This reduces down to this matrix. Okay, and so there are going to be some vectors if we augment with them that will have an inconsistent solution. So because we see there's a row that has all zeros in it, we're not going to have the span that's all of R3. So instead, it's going to be a plane. One way we can express this plane is by actually trying to write down the set of all solutions. So let's take a look. So let's find all vectors x, y, z that are in the span of these three vectors. We'll learn other approaches as well this semester. Okay, and I'm going to do this row reduction by hand. Notice there's no particular order when we're writing this. So when I write down my vectors, I'm going to just put them in an order that's a little bit easier for me to think about. So I'm going to start with the second vector, and then 1, -2, 2, and 5, -6, 4. And we're augmenting with this vector x, y, z. Okay, so we want to know, when do we have a solution? Oops. Okay, we're going to do a little bit of row reduction here. Row 3 is going to be row 3 plus row 1. And so we get 1, 1, 5, x, 0, negative 2, negative 6y, 0, 3, 9, x plus z. Okay, so we've cleared out all of the values underneath 1. Okay, next let's divide row 2 through by negative 2. So we're going to do negative a half times row 2. So we get 0, 0, oops, nope, 0, 1, 3, negative y over 2, 0, 3, 9, x plus z. Okay, we want to get rid of the 3 underneath it. So we're going to subtract 3 copies of row 2 from row 3. We're hoping to find when this system is consistent. Okay, so if we look at the things that are to the left of the augment, 3 times row 2 is 0, 3, 9. So we get all zeros on the left. Then we're going to do x plus z minus 3 times row 2, which was negative y over 2. Okay. Okay. And let's focus in on this last equation. So we're going to have a consistent system and solutions. Our vector is in the span. If this last row is 0, 0, augmented with 0, which corresponds to the equation 0 equals 0. If this right-hand side is equal to anything other than 0, there, our vector won't be in the span. It won't be a consistent system. So we have a consistent system as long as x plus z minus 3 times negative y over 2 is equal to 0. So a row of all zeros. Okay, so that means that we can express this as x plus z plus 3 halves y equals 0. And this is an equation of a plane. Okay, so we can put in values for example, for x and z, and it'll tell us a corresponding the y value on the plane. Good. Okay. So this gives us a way of describing the span.